Thanks for joining me today. I'm going to take a few minutes to illustrate the proof of the Collatz conjecture that's presented in the short story Bits of Complexity. The Collatz conjecture, it says, take a number. If that number is even, divide by 2. If it's odd, multiply by 3 and add 1. And that if you keep repeating this for any number, you will eventually reach 1. First, let's do a thing that nobody has ever done. Separate the original odd or even actions completely. Instead of doing that, we're going to use the formula 3n plus the least significant bit that I'll denotate LSB and never divide by 2. The stopping condition is that the number has reached a perfect power of 2 to the nth. Let's define the least significant bit. Given a binary representation of a number, the least significant bit is the smallest power of 2 in that number. And so now, let's look at an example. Consider 36. In binary, that's 4 plus 32, or 2 to the power of 2 plus 2 to the power of 5. Its least significant bit is 2 to the power of 2. Let's have a detailed look at that. Making a column for each power of 2, the binary representation looks like this. If we were doing the original Collatz, we'd divide by 2 and get 18, and then divide by 2 again to get to 9. Then we'd apply 3n plus 1 and reach 28. Here, like this. With the new formula of 3n plus the least significant bit, we get to 112. That's 3 times 36 plus 4. At this point, I'll point out that 112 is exactly 4 times 28. And if we did the division of this after this operation, we'd be in the same place. And I also want everyone to clearly remember that any number that is 2 to a power can be divided by 2 that number of times to reach 1. So when we separate the even or the odd actions, the end result will have the same overall change, but we no longer have to consider division in the problem. We see that the divide by 2 step is not significant in the overall solution to the Collatz, that it's trivial. So let's get back to this 3n plus the least significant bit. 3 times n plus the least significant bit is like taking n plus 2 times n plus the least significant bit. And we can do that in addition in binary like this. The value is 112, which is 2 to the power of 4, 5, and 6. 16, 32, and 64. We also reach 112 when we apply the transformation to 37, 2 to the 0th plus 2 to the 2nd plus 2 to the 5th. 1 plus 4 plus 32. Here's its representation. Let's put those two side by side. 3 times the original value plus the least significant bit equals 112. And let's follow this example all the way to the end. When we apply 3n plus LSB to 112, we get 352. We also reach 352 from 116 and 117. When we apply 3n plus the least significant bit to 352, we get 1088. We also reach 1088 from 360 and 362. When we apply 3n plus LSB to 1088, we get 3328. We also reach 3328 from 1104, 1108, and 1109. When we apply 3n plus the least significant bit to 3328, we get 10240. We also reach 10240 from 3072, 3392, 3408, 3412, and 3413. And lastly, when we apply 3n plus the least significant bit to that, we get 32768, which we also reach from 10752, 10880, 10912, 10920, and 10922. And you'll notice that 32768 is a perfect power of 2 to the 15th. So we stop here. Let's look at that progression graphically. And now that you've seen this, we can talk about getting to a proof. Let me go back to the data for 3328 that goes to 10240. Remember, we get to 10240 from these other values as well. Instead of looking at the numeric values, consider each number as some arbitrary data. When we calculate 3 times that number plus the least significant bit, we lose data. How can we know or prove this? We examine the reversibility of the transformation. In this specific example, 6 numbers all transform into 10 to 40, and that conversion cannot be reversed. There is no information present in 10 to 40 that indicates which of those was transformed into it. So let's formalize this. Let's start by saying this conversion happens every time after the first 2 applications of the function for any series of numbers. Look back at the spreadsheet. Notice how all of these numbers share the same base, but then have a leading 1 and 0 before it. That pattern repeats until the smallest possible least significant bit has been used. The formal proof presented in bits of complexity explains this in mathematical terms, and the loss of data happens repeatedly, over and over. So, if a number keeps transforming and losing data, it's not possible for loops to occur. There's no way to return to a previous state of information when the only change to the data is this loss of information. And lastly, consider a finite number that can hold a finite amount of information. If information is lost every time, the amount of information present will eventually revert to a base state, notated as 2 to a power, or 1 bit of information, the number 1. Or consider it another way. The only way to not end would be to have a number that contained an infinite amount of information, that even after removing a nearly infinite amount of information, it still possesses an infinite amount. That doesn't exist. The practical tack is also to realize that there would never be a single number or series of numbers. There would be an infinite sequence of numbers and variations on those numbers and all similar numbers. And so, if all numbers must eventually transform into 2 to a power, and we know that 2 to the power is reduced to 1 by dividing that number by the number of power times, we can say that the Collatz conjecture has been proven. I'd like to wrap this up by sharing 2 interesting aspects that can now be seen. The first is a chart. If you count all the numbers that converge at each power of 2, it looks like this on a log scale. The blue line is 2 to a power, and that shows as a straight line on a log scale graph. The line across the bottom is the power of 2. That shows as a curve on a log scale. The green line, that's the count of all the numbers that end their chain of results at 2 to that power. The purple line starts at the number of solutions for 2 to the 10th and grows at the rate of 1.3. This is a first approximation. Here's the fun. If you chart out at 4/3 to the power, that is nearly exactly the growth of the number of solutions. The black line for its value is nearly covered by the green. You can see it poking out at the top and the bottom. In some conversations around Collatz, the concept of unity comes up. If we simply remove the ending state, we can see that any perfect power of 2 will continue to transform to a larger perfect power of 2, as seen here. One might say that all numbers merge at 2 to the infinity, but that's not quite the case. Numbers that merged into 2 to an even power are distinct from those that merge into 2 to an odd power. And so we have 2 graphs of numbers that expand forever. And here's a graph of all numbers that merge into 2 to the 15th. I have to admit, I love this graph. Okay, here's a third thing to wrap things up, an image from bits of complexity. All the values reaching 2 to the 19th and 2 to the 20th. And again, thanks for joining me today. Take care.